This is our second video on the topic of applications of second order differential equations. We're mainly focusing on applications in mechanics in these videos. There are some other applications discussed in the text. In the last video, we pretty thoroughly covered what happens with a mass spring system when you have no damping and no external force. We got a pure oscillation in that case. And our plan for the rest of these videos, pretty much following the text, is to gradually increase complications, more realistic physical factors, which are going to, of course, complicate our solution, and so we're just going to see what happens. The first complication we're going to introduce is we're going to include damping now, and we're still going to assume that there's no external force acting for now, but we're going to assume that we have a damping force acting on the mass that's proportional to the velocity. So if the velocity is going in the positive x direction, a is a positive constant, that would produce a damping force in the negative direction opposite to the velocity. And similarly, if the velocity is negative, the damping force will be positive, tending to oppose whatever the velocity is, whichever way the object is moving. So to set up our differential equation, we're still working with Newton's second law. Mass times acceleration is the total force. And now we have two forces acting on our mass, a spring force and a damping force. We assume, as in the previous video, that the spring force is given by Hooke's law, and we include the assumption that we just made about our damping force. So that gives us our second order differential equation. Fortunately, once again, we're ending up with a constant coefficient linear homogeneous differential equation, which is relatively easy to solve. Putting that in standard form by putting everything on the left-hand side, that's our differential equation model in this situation for a mass on a spring with a damping force and no other external forces. For the solution, we proceed in the usual way, find the characteristic equation, which would be that, and the roots of our characteristic equation then, by using the quadratic formula, are given by that expression. And just like we had in section 2.2, there's three cases depending on the roots of that equation, and we're going to try to understand what happens physically in each of those three cases. If the expression under the radical is zero, or pardon me, if the expression under the radical is greater than zero, physically that would mean that your damping force is relatively strong. A is the parameter here, which reflects how strong the damping is. The larger A is, the stronger the damping force, as we can see from up here. So if your damping is relatively strong relative to the other parameters in the problem, that expression is going to turn out to be positive, and you're going to end up with two real roots. Case 1, lambda 1 and lambda 2 are both going to turn out to be negative in this type of problem, as we will see shortly when we start looking at some examples. Now, if your damping force exactly balances the other parameters in the problem, that produces a situation that we call critical damping. In that case, the expression under the radical is 0, and this is what we referred to as case 2 earlier in the chapter, where we're ending up with a repeated real root, a root of multiplicity 2, and in that case our general solution has that form. The third case is maybe the most interesting one, where the expression under the radical is less than 0. Then we're ending up with complex conjugate roots using the same notation that we used earlier in the chapter. Alpha turns out to be negative a over 2m, and beta turns out to be this. And from the expression we had up here for by using the quadratic formula, then we get our general solution by plugging into the usual alpha beta type formula that we learned for this situation earlier in the chapter. Now we're going to look at some examples to make this a little more concrete of each of these. In example 4, we'll look at an example that's going to turn out to have strong damping. So we'll look at this initial value problem, and we'll start by finding the solution of the general solution of the homogeneous DE in the usual way, writing down the characteristic polynomial, and then if we divide through by the common factor of 2, it's a little bit easier to work with, and it's fairly easy to see that that quadratic factors here. So we're in case 1. We have 2 distinct real roots, which are both turning out to be negative, as was claimed on the previous slide. In this video, I omitted the details of going from your general solution to the solution of the initial value problem. We've done that a lot, that kind of thing a lot already in this chapter. If you feel like it, you might want to check that those initial conditions which I gave you imply C1 equals 5 and C2 equals 2. You can check that if you feel like it. Assuming that, then the solution of that initial value problem is 5e to the minus t plus 2e to the minus 4t. And both of those terms are, of course, approaching 0. If you had a situation where C1 and C2 had opposite sign, you could have a solution trajectory that passed through the equilibrium at most one time. Here, our solution doesn't pass through the equilibrium at all, since both terms are positive and decreasing. So, but either way, you're not going to see much of an oscillation in this type of situation, because physically you've got strong damping, and the damping is physically driving your solution to 0 as time goes on. So if you plot that, you're going to have something like this, where your solution starts out at 7, but because of the strong damping, it rapidly approaches the equilibrium. Of course, it never exactly reaches the equilibrium, but what we're saying is x equals 0 is a horizontal asymptote, which the solution approaches. Actually, it approaches it fairly rapidly here. Now for another more concrete example, we'll look at example 5 here. So we'll look at this initial value problem. This is going to turn out to exhibit critical damping. And again, we start by finding the general solution by writing down the characteristic equation. Once again, we have a common factor of 2, which we divide out. So lambda is going to be the root or roots of that equation. Again, we can easily factor that. We see we're indeed dealing with the case 2 situation where we have a double root of multiplicity 2. So that gives us that expression for the general solution. Again, I omitted the details of going from the initial condition to determine the value of the constants C1 and C2. I omitted that detail in this video. That's something that we hopefully know how to do at this point in the chapter. So you can check that if you feel like it. It turns out C1 turns out to be 2 and C2 turns out to be 4. So the solution of that initial value problem turns out to have that form. Because those guys have opposite signs, we do pass through the equilibrium exactly once in this situation, but again, with the critical damping, we don't really see much of an oscillation happening. Both terms are approaching 0 as t approaches infinity. And once again, x equals 0 is a vertical asymptote, a horizontal asymptote for our solution, which makes sense physically. If a system is damped and there's no external force, the system should lose energy, and that's what we see from our analytical solution from the formula and from the graph.